Good morning, everyone. Today, we are exploring one-dimensional convective heat transfer, a key mechanism in thermal engineering. Now, in this case, we are going to discuss what is meant by a convection mode of heat transfer. This convection occurs when heat is transferred between a solid surface and a moving fluid, combining conduction within the fluid and the fluid's motion. This process is vital in systems like car radiators, HVAC units, and industrial heat exchangers. In one-dimensional convection, we simplify the analysis by assuming heat flows in a single direction, making it easier to model and solve real-world problems. Now we will cover the Newton's law of cooling, which governs convections, and discuss the types of convections. Which are the natural convections and a forced convection or a mixed type of convections. We will also explore the concepts like the thermal boundary layer, dimensionless numbers, and practical applications. By the end of this lecture, you will understand how convection works, how to quantify it, and its role in engineering designs. Whether you are curious about cooling electronics or optimizing the industrial process, this topic is very much essential. So let's start and see how fluid motion drives heat transfer in systems around us. Now let's start with the basics of convective heat transfer. Convection happens when a moving fluid like air or water transfers heat to or from a solid surface. It involves two processes. First is conduction, where heat moves through the fluid near the surface, and fluid motion, which carries that heat away. For example, when the hot air rises from a radiator, its convections at that location. This process is driven due to the temperature difference between the surface and the fluid. Convection is governed by Newton's law of cooling, which we will explore in the next. It is a critical mechanism in engineering which is used in everything from cooling the car engines to designing efficient heating, ventilation, and air conditioning systems. Convections can be natural, caused by density difference, or forced convection, which is because of the fans or pumps. In one-dimensional convection, we assume heat transfer occurs in a single direction, simplifying analysis for the system like flat plates or pipes. Understanding convections helps the engineers to optimize the thermal performance and energy efficiency. Now let's move to Newton's law to see how we quantify this process. Now let's focus on Newton's law of cooling. It is the foundation of convective heat transfer analysis. The law states that the heat transfer rate Q is proportional to the surface area, the temperature difference between the surface temperature and the fluid temperature, and the convection heat transfer coefficient H. Mathematically, it's Q is equal to H multiplied by A multiplied by Ts minus T infinity. Here, Q is in watts, H is in watts per square meter Kelvin, and A is in square meters. The convection heat transfer coefficient H depends on the factors like fluid properties, flow type, and surface geometry, making it a critical parameter. For example, When hot plates cools in air, heat is transferred to the air proportional to temperature difference. This law allows engineers to calculate heat transfer in systems like radiators or heat sinks. Understanding H is key to designing efficient cooling systems as it determines how effectively heat is removed. Newton's law simplifies convex or the complex convection process into a manageable formula, guiding applications from electronics to industrial process. Next, we will explore the different types of convections. The convection comes in three main types: natural convection, forced convection, and mixed convection. Natural convection occurs when fluid motion is driven by density differences due to temperature variations. For example, when you boil an egg, hot water rises because it is less dense, which creates a circulation. Forced convection, on the other hand, involves the fluid motion induced by external forces, which help with help of fans or pumps. Think of a car radiator where a fan pushes air to cool the engine. Mixed convection combines both, often seen in systems where natural and force effects interact, such as in case of heating, ventilation, and air conditioning setups. Now, each type has unique characteristics, and the forced convection is used where high heat transfer rates are needed. Mixed convection requires careful analysis to balance both effects. Understanding these types of convections helps the engineer to choose the right approach for a given system, whether it is cooling an electronic system or designing an heat exchanger or a radiator. Now let's look at the assumptions that simplify the one-dimensional convection analysis. To analyze one-dimensional convection heat transfer, we rely on several assumptions. To simplify the problem, first, we assume heat transfer occurs in only one direction, such as perpendicular to flat plate or along a pipe axis. This reduces the complexity by focusing on a single flow path. Now, second, we assume steady state conditions, meaning the temperatures and the flow properties don't change over time. This is common in systems operating at equilibrium like a radiator under constant load. Third, we assume the fluid properties such as viscosity and thermal conductivity are constant, which is reasonable for small temperature ranges. Finally, we assume no internal heat generation in the fluid, so no chemical reactions or other heat sources complicate the analysis. These assumptions allow us to apply the Newton's law of cooling and other models effectively. They are applicable in scenarios like cooling flat surfaces or designing the heat exchangers. By simplifying the problem, we can focus on the core physics of convections. Next, we will explore the thermal boundary layer, which is a key concept in convection. Now, coming on the important concept of the thermal boundary layer. It is a critical concept in convection heat transfer. It's a thin region near a solid surface where temperature gradient exists, transiting from the surface temperature to the bulk fluid temperature. For example, when the air flows over a hot plate, the air near the plate warms up, creating a boundary layer where the temperature changes rapidly. The thickness of this layer depends on the fluid velocity, viscosity, and thermal properties. Faster flows or higher thermal conductivity reduces the layer thickness, increasing the heat transfer coefficient H. The boundary layer directly affects the heat transfer coefficient H, as the steeper temperature gradients within it enhances the heat transfer. In engineering, understanding the thermal boundary layer helps to optimize the systems like heat exchangers or cooling fins, where maximizing the heat transfer is crucial. For instance, in a radiator, a thin boundary layer ensures efficient cooling. This concept also ties with the flow type, that is, whether the flow is a laminar or turbulent, which we will explore further with the dimensionless numbers. The thermal boundary layer is a bridge between the fluid dynamics and heat transfer, guiding efficient designs. So let's move to the dimensionless numbers in the next slide. Dimensionless numbers are essential for analyzing convection heat transfer. The Nusselt number represents the ratio of convective to conductive heat transfer across the boundary layer. It is defined by Nu is equal to HL by K, where H is the convective heat transfer coefficient, L is the characteristic length, and K is the fluid's thermal conductivity. A higher Nusselt number indicates a stronger convection. The Reynolds number, Re, determines whether the flow is laminar or turbulent based on the velocity, density, viscosity, and length scales. A low Reynolds number indicates it is a laminar flow, while high Reynolds number indicates it is a turbulent flow, which enhances heat transfer. The Prandtl number is the ratio of momentum diffusivity to thermal diffusivity, reflecting how momentum and heat is spread in the fluid. The Nusselt number is a function of Reynolds number and Prandtl number, as Nu is a function of Re and Pr, allowing us to correlate the fluid flow and heat transfer. These numbers simplify the complex convection problems, enabling the engineers to predict the heat rates in a system like pipes or the flat plates. They are critical for designing efficient cooling systems or heat exchangers. Next, we will apply this concept to the heat transfer over a flat plate. Let's examine convective heat transfer over a flat plate, a common scenario in engineering. The Nusselt number correlates the heat transfer coefficient H to flow conditions. For a laminar flow, when the Reynolds number is less than 5 into 10 raised to 5, the Nusselt number is given by Nu is equal to 0.664 multiplied by Reynolds number multiplied by under root of L multiplied by Prandtl number raised to 1 by 3. Now here, the Reynolds number is based on the plate's length and Prandtl number is given by PR. For turbulent flow, when the Reynolds number value is more than 5 into 10 raised to 5 and less than 10 raised to 7, the Nusselt number is given by Nu is equal to 0.037 multiplied by Re, that is Reynolds number raised to 4.5 multiplied by PR, which is Prandtl's number raised to 1.3. For combined laminar and turbulent flow, the Nusselt number is given by 0.037 multiplied by Reynolds number raised to 4.5 or 4 by 5 minus 871 multiplied by Prandtl number raised to 1 by 3. These correlations allow us to calculate what is the heat transfer coefficient H, which determines the heat transfer rate via Newton's law of cooling. Laminar flow has smoother, less efficient heat transfer, while turbulent flow enhances mixing, increasing the value of H. These formulas are used in the applications like cooling electronic boards or designing heat exchanger plates. By understanding how Nusselt number depends on Reynolds number and Prandtl number, engineers can predict and optimize the heat transfer for specific flow conditions. This analysis is critical for systems requiring precise thermal management. Next, we will explore the practical applications of one-dimensional convection. One-dimensional convective heat transfer has numerous applications in engineering. First, it's essential for cooling electronic components like computer chips, where air or liquid convection removes heat to prevent overheating. The heat sinks, which rely on the forced convections which have to maximize the heat transfer. Second, heat exchangers in the industries such as those in the chemical plants or the power generation use the convections to transfer heat between the fluids, often through the plates or tubes. Third, the heating, ventilation, and air conditioning systems depend on convections to heat or cool buildings, using fans for the forced convection or the natural convections for passive systems. Finally, the engine cooling through radiators, as in the cars, uses the forced convections to dissipate the heat from the engine, ensuring the optimal performance. These applications highlights the convection role in improving the efficiency, safety, and performance, whether it's maintaining comfortable indoor temperatures or protecting the critical machinery. One-dimensional convection analysis is a vital tool. By applying the Newton's law and dimensionless numbers, engineers can design systems that manage the heat effectively. So let's conclude with the summary of the heat transfer mechanism in the next slide. Now, to summarize, convection heat transfer is important in thermal engineering, which is driven by the fluid motion and governed by Newton's law of cooling. In one-dimensional convection, we simplify analysis by assuming the heat flow in one single direction, making it easier to model the systems like a flat plate or a car radiator. We have explored natural force and mixed convections, the thermal boundary layer, and dimensionless numbers like Nusselt, Prandtl, and Reynolds, which quantify heat transfer and flow behavior. These applications range from cooling electronics and engines to designing HVAC systems and industrial heat exchangers. These principles enable engineers to optimize the thermal performance, reduce energy waste, and enhance system reliability. In industries like automotive, electronics, and manufacturing, convection is critical for innovations. I hope this lecture has deepened your understanding of convective heat transfer and its impact. For the next time, think about how convection applies to a systems you encounter, like car radiator or an air conditioner. Thank you, and let's keep exploring the science of heat transfer.